Hello friends, welcome once again to our channel. And in this video, as we know, we have to see about the Reynolds number. If you remember, in the previous video we have talked about this Reynolds number. So this Reynolds number, there we have denoted by the K, and there we actually found what we have found. We have found the critical velocity equation. So critical velocity, we know we have written like this: critical velocity is equal to K times the coefficient of viscosity and divided by rho into the R. So here we define this K as Reynolds numbers, but in most of the books you found that you will find that this is denoted by R suffix E. So it is just a different notation, we can say. So you can denote sometime most of the times R suffix E. So that indicates the Reynolds number. Okay. So this K, why using this particular formula, that already we have seen in the previous video. So if you haven't watched that video, I will post the link of that video in the description box of this particular video. So please watch that and let us understand there also how did we found this velocity, critical velocity, and in which how did we got the Reynolds number. Okay, so this is nothing but the R suffix E now. So if we rearrange this equation and gets converted into the Reynolds number form, so how it becomes? It actually becomes the rho into critical velocity Vc into the dimensions of the tube, that means radius of the tube, and then in this case the coefficient of viscosity eta will go to the numerator. So this indicates the formula for Reynolds number. And if you see, if we substitute the dimensions of rho, velocity, and the radius of the tube, and in the denominator if we substitute the dimensions of all the particular coefficient of viscosity, then you will find that this Reynolds number is actually a dimensionless quantity, right? So that also we can prove first of all. So let me tell you how it comes. It is a constant or it is a dimensionless quantity. So as by this particular formula we can see like one. So dimensions of Reynolds number must be the dimensions of density, right? Then dimensions of our velocity, that is critical velocity, and dimensions of the radius, and divided by the dimensions of eta. Okay, so if we do all these things, then we will find the dimensions of our Reynolds number. Okay, so if you see this density, we know it is generally measured in mass per unit volume, we call it as density. Or when we talk about this particular density, it actually have the dimensions 1 in length and -1 in time. Okay, similarly this particular actually this is for velocity, right? Mass meter per second velocity, and if we multiply this with the density meter or sorry, we can say mass per unit volume. So that means not L, so we can write M, and volume is obviously again meter cube, so I can write L minus 3, and what will be the dimensions of that is simply L. Okay, and if we divide this by the dimensions of our coefficient of viscosity, as we have found out in the very first video, so 1 in mass, -1 in length, and -1 in time. So if we cancel these things, or if you see this 1 in mass will get cancelled with this mass, then the -1 in time, so -1 in time and -1 in time will get this L, and obviously we have here 2 L's in numerator. So L and L, we can have L2, and 2 minus this 3, it might be -1, and that -1 will get cancelled with the denominators minus L. So therefore we can have the dimensions of this Reynolds number, we can write it as 0 in mass, 0 in length, and 0 in time. So basically it is a dimensionless quantity. Okay, it is a dimensionless quantity, right? Now come to the point how we can define this Reynolds number, and that is what I have written here also: the inertial force divided by the viscous force. Okay, whatever may be the inertial force, that means this density into velocity and the diameter or the radius of the tube is indicating the inertial force. Okay, that means this liquid is moving within the tube of diameter d, and with a critical velocity or with velocity v, and if the density of the liquid is rho, then simply whatever may be their product, we call it as inertial force, And the viscous force, we know viscous force represents the viscosity coefficient, moreover the coefficient of viscosity. So, we can write viscosity coefficient here, and therefore, this Reynolds number, again here mu is represented by the viscosity coefficient, but yes, we can mu represent either mu or by eta again, right. So, here as I have drawn in here in this diagram also, the velocity of the topmost layer will be maximum, and as you can see from this diagram also, the velocity goes on decreasing towards the bottommost layer or towards the this is what we can say, the steady surface or the fixed surface. And if we know the value of all these three things, that means rho, v, d and the coefficient of viscosity of liquid, we can exactly get the Reynolds number. Okay. Again, one more thing we can write in the Reynolds number in terms of the kinematic viscosity. So, kinematic viscosity means the coefficient of viscosity divided by the density. So, this equation here we can write this as simply this and this kinematic density viscosity is denoted by nu, and therefore, we can rewrite this Reynolds number as I have written here VL, because length we can say it is in the numerator, and whatever may be this mu by rho by mu, we can write it as the kinematic density, or mu by rho is actually mu by rho is and therefore, it is in the denominator. So, VL divided by nu, that is the kinematic viscosity. So, we can write it as, or we can say in general from this formula also, the coefficient of viscosity per unit density, we can call it as kinematic viscosity. Okay. And whatever may be this Reynolds number per foot we can calculate as the Reynolds number, because we know whenever we are talking about the fluid, how it passes from one point to other point, and moreover we have to do this for the longer distances and all. So, we must know what is the Reynolds number of a particular liquid through a particular tube, and moreover per feet also we must know. So, therefore, we can call write that as REF, again obviously here is the space. So, Reynolds number per foot, and it is simply velocity divided by these kinematic viscosity, and it is denoted by nu. Okay. So, obviously, that means we have get this from this particular equation only. This L we have bring to the other side, means already it was simply Re is equal to VL divided by nu. So, we can take this Re divided by L, that L represents the length of the tube, and yes, therefore, the Reynolds number per unit length or per feet, it is simply this one, and V divided by nu. That means, if you know the velocity and the nu, that is kinematic viscosity of the liquid, then we can exactly get what will be the Reynolds number per feet. Okay. Now, this is all about the Reynolds number. Now, let us see some applications and the significance of this Reynolds number. And yes, so as we know, this is the formula for Reynolds number, we have already seen in our first slide also. So, here this actually helps us, this Reynolds number can interpret the ratio of inertial to the viscous effects, and at low Reynolds number, if you have a liquid with low Reynolds number, then we can say the viscous effect is comparable to inertial effect, and the flow behaves in an orderly manner if we have the low Reynolds number. So, it actually has a laminar flow or the streamline flow. That means, if you have a liquid which has low Reynolds number, then we can say it can possess, or it almost possesses, the laminar flow or the streamline flow. Okay. Now, here you can see what is the actually the streamline flow. So, this first case is actually the streamline flow or the laminar flow, right. This the second is what actually the turbulent flow, or we can call it as the transition flow, B and C. So, this is actually the laminar flow. Okay. So, if you want the laminar flow from any liquid, so it is necessary to it must have the low Reynolds number, or in vice versa we can say, if you have the low Reynolds number, we can expect the laminar flow of that particular liquid, and if you have the high Reynolds number, then the viscous effect is insignificant compared with the inertial effect, and the flow pattern is irregular, unsteady and random, and that type of flow, as it is shown in this particular C diagram, it is we call the turbulent flow. So, all these guesses or all these things we can guess, or we can judge the flow by only the Reynolds number, and that is why the Reynolds number have that much significance as far as the viscosity of that particular liquid is concerned. Okay. And yes, this is all about the significance of Reynolds number and its application, and again how the Reynolds number has to be derived from the critical velocity definition and what are its dimensions and all. Okay, so I hope you got this point. This is very small article but important one, and yes, after this article we will be meet in next video with Bernoulli's theorem, and till then take care and keep learning. Thank you for watching this video.